Greetings, grade 10s. Welcome to this 8th lesson. We are going to be looking at macromolecules, specifically at graphite and also at diamonds. So like I said last night, the other recording that I had done, it didn't finish sending, so I have to record again, but it's okay. So in the previous lesson, in lesson number 7, we were looking at the Vesper theory, valence shell electron pair repulsion theory, and how it was affecting the way in which the molecules of methane, ammonia, water, how their shapes appeared based on the number of single covalent bonds and the number of lone pairs that were there. It was all affecting the shape of those covalent molecules. So we also have other covalent molecules which are now described as giant covalent molecules. Macro means very big, right? It just means big, but we can also say very big. So there's macro, then there's micro. I'm sure you've seen microscopes and how microscopes allow us to see things that are micro, which means they're extremely small, cannot be seen by the naked eye, whereas macro then refers to anything that you can see with the naked eye, right? Because relativity, right, in terms of relative to the very small particles, anything that you can see with your naked eye is actually extremely big. Relativity. You can Google relativity if you want. Right, so today we are looking at graphite. The objectives of this lesson, by the end of this lesson, we should be able to identify macromolecules. Macromolecules describe the structure of the allotrope of graphite. You'll also be able to actually describe the structure of diamond as well, even though I'm going to look at it specifically in the next lesson. Explain the uses of graphite in relation to its properties. So like I said, it's a very simple concept. So just pause the video for just 30 seconds or so, look at the objectives and see if you have any idea what carbon graphite is and what macromolecules are. Okay guys, so let's look at the term allotropy and allotropes. What are allotropes and what does it mean? I'm sure this is a new word, and it's probably the first time some of you have encountered that word. So an allotrope refers to different structural forms of the same element in the same physical state. What are we looking at right now? Right now we are looking at there, it says allotrope, and these are allotropes of the element. Which element has the symbol C? The element with the symbol C is carbon. If you go onto the periodic table and you look for the element with the symbol C only, that is carbon. Carbon in the solid state can be found as diamond. It can be found as graphite. It can also be found as fullerenes, but we are not going to look at fullerenes at all, right? We're going to actually talk about them when we talk about them in nanochemistry. But right now, under giant covalent structures, it's not yet necessary. So diamond and graphite. Different structural forms of the same element in the same physical state. What are we trying to say when we say we have these different physical forms of the same element? It just basically arises from the manner in which the atoms are arranged. I hope you are listening. Because you guys you've been doing this thing where you don't listen to the audio. You don't listen to the explanation, and then you get confused. The arrangement, the manner in which those carbon atoms are arranged, brings about different substances. Just by arranging these carbon atoms differently in a different arrangement, just now I will show you like this is a structure. This structure is of graphite, right? If I show you on the video here, the structure of diamond is clearly different from that of graphite, but they are both allotropes of carbon. And the moment they are arranged differently, it brings about different substances with different what? Physical properties. Okay? So that's what allotropes are. That's what allotropes are. And carbon is one of those elements which shows allotropy, because you can have graphite, you can have diamonds, you can have fullerenes. Okay? Then under giant covalent structures, in the next lesson, we will also look at silicon oxide, because it also forms these giant molecular structures. Okay? So let's look. We have a table here that is showing us the differences between the allotropes of carbon, that is diamond and graphite. So just have it, just give yourself, I'll pause the video on my side, you pause the video, just have a look at the differences between the carbon allotropes, the diamond and the graphite. Okay guys, I hope you were able just to pause for a few minutes, and yeah, maybe just 1 minute, and had a look at the differences between diamond and carbon. Okay, so let's also look at an important aspect when we look at these covalent structures. These giant covalent structures are covalently bonded. They are covalently bonded because, remember, these are bonds that are taking place between carbon atoms, right? Carbon atoms are non-metallic atoms. Therefore, they form covalent bonds. Yeah? Covalent bonds, because if they are nonmetals are joined together using what we call covalent bonds. But if it was a nonmetal and a metal, what type of bond would be formed there? You would then form an ionic bond. So these are giant covalent structures, but they are covalently bonded. Therefore, those covalent bonds are very strong. It also helps explain the properties, right? The properties of graphite and the properties of diamond. I'm sure you saw how they have very high melting points, right? They have very high melting points, and if we look at diamond, it's very strong. So each carbon atom in the diamond is covalently bonded to 4 other carbon atoms, right? I will just play through this quickly. You use it to refer to it in the next lesson when we look at diamond specifically. What I'm more concerned with in this lesson will be the graphite. So let me just push this video. Right. So now let's look at graphite. As you saw with the diamond, each of these carbon atoms is bonded to 4 other carbon atoms. Why is this important? Why is it important that we say carbon is bonded to 4 other carbon atoms? If you draw the Bohr diagram of carbon, you will find that it has 4 electrons in its outermost shell. Therefore, it's able to form 4 bonds. 4 bonds because it has 4 electrons, right? It can form 4 single bonds, or it can form 2 double bonds, right? So this carbon, all of its electrons have taken part in bonding, okay? But look at the graphite now. The graphite, its structure, on the structure of graphite, this one, I hope when I'm touching it, the little dot is showing. On the carbon is bonded to 3 carbons only, right? To 3 carbons only. And that then results in 1 electron being left, and it's not taking part in any bonding, right? So here we're just looking at the structure, how the graphite is arranged, right? The graphite is arranged in these hexagonal structures, but then they are there in flat sheets, layers, one layer over the other, one layer over the other. You'll find that under the uses, we'll talk about the uses. One of the uses is that graphite is used in pencils. If you look at that black thing that's in your pencil, that is pencil lead. It's a mixture of graphite and clay. Graphite and clay used to make pencil lead, right? Used to make pencil lead, and then you use it to write. And because it's in these layers. These layers peel off. When they are peeling off, that's what you actually have. You're actually leaving layers of graphite on the paper. That's the whole. That's what you're doing when you're writing with a pencil. You are basically leaving layers of graphite on the paper. Okay, so let's proceed with this one. What I was saying was carbon, and why are these layers able to peel off easily? Because they are held together by weak forces. They're not held together by covalent bonds. The different layers, the carbon-carbon atoms, held together by covalent bonds. But the different layers held together by weak electrostatic forces, just weak electrostatic forces. VDW, Van der Waals forces. I hope I'm correct on that one. Right? So they are held together by weak forces. Right? They're held together. And that's why it's easy for you to just, when you're writing for the graphite, to just slide off. It's just coming off the pencil. With the diamond, you have no chance. You have no chance of breaking or removing a layer of that diamond, because that is one of the hardest materials known to man, right? Diamonds. That's why they last so long. Ladies, I know it's you, Maria, Tuna, Elenate, Rita. You guys, you're always there in the lessons. I know you guys. I know you guys love diamonds. all the ladies love diamonds, right? So when you get yourself a diamond ring or you get yourself a diamond necklace, you know that thing is gonna last, right? If someone gets you a diamond necklace, that thing is gonna last until, it was probably there before you were born. It probably will still be there after you die. That's how strong diamond is, okay? Let's look again. So the point I was making is there are free electrons. There's one free electron now that is left on the graphite molecule, right? When you're having graphite, because only 3 carbons have taken part. So one spare electron is left. And now observe that there are thousands of these carbon atoms, thousands, millions of these carbon atoms that are there. And so they now all have a delocalized electron. And this delocalized electron then allows for the graphite to be able to conduct electricity and to conduct heat, because the electrons can now move through the structure, right? It conducts. It's a poor conductor, but it does conduct. It's a poor conductor of electricity, so don't end up thinking that maybe it's the best conductor of electricity. We know that copper and the other metals are the best conductors of electricity, but carbon, as a non-metal, is one of the few non-metals that's actually able to conduct electricity, and that is because of the presence of these delocalized electrons, right? These delocalized electrons. So let's also look now at, so the structure. This is the main structure. This is just like this one. There's one that's the main structure, small section. Main structure, small section. The small section is just a cutoff, right, of one of the parts of the main structure. So if you read up on it, we're also going to discuss, it's a simple concept. Then the uses. The uses, you then get to see them from the properties. The properties tell you the uses. Okay? So if you understand the properties of a material, you then understand its uses. Okay? We've already said that it's used to make pencils, right? The slippery property, and then the fact that the layers of carbon are able to come off, right? They're actually known as graphene. We'll talk about graphene and talk about nanomaterials as well. So the layers of carbon are able to come off. That allows it to be used as a pencil. Then electrodes. I hope you guys know what electrodes are. If you've ever seen batteries, if you take your cell phone has a lithium-ion battery in the back of it. Okay? That lithium-ion battery has electrodes inside of it. Electrodes are used they allow electricity to move. Okay? So you have the battery is effectively an electrolytic cell that allows charges to move from a positive to a negative side, right? So inside of your lithium battery, there is a graphite rod that is there, right? and this, as is written here, has created a very high demand for carbon, because we know that most of the devices are being powered by lithium-ion batteries, right? Everyone is always looking for power. Where can I charge my phone? I think that's the first thing that people think about whenever they get somewhere. Is there power here? Where can I charge my phone? And then the next thing is there Wi-Fi? So electrodes, graphite. Electrodes are made of graphite because it's able to conduct electricity. As a lubricant, I'm sure we know of lubricants, the liquid ones. We are more used to the liquid ones. And if you think of oil, how we place oil on different, even if it's on our cars, on wheelbarrows, different machinery, those are liquid lubricants. But then the apparatus, I'm sorry, I can't remember. I can't even think of a single one. But if you Google, please Google, appliances which would require solid lubricants. And if there is a need for a solid lubricant, they are going to use graphite. There are times when you can't use a liquid, probably interferes with the mechanism or the system. So you then have to use a solid lubricant. And when you have to use a solid lubricant, who do you tend to? You tend to your graphite. You tend to your graphite, and it plays that role perfectly, right? So physical properties, dark gray, soft, good conductor of electricity. Okay? Then properties of diamond, we'll look at them in detail in the next lesson. So, guys, that's lesson 8, macromolecules, graphite, objectives. I'm sure we've covered all of the objectives that we set out to cover. I'll see you guys basically in an hour or so, because this is just an hour before the lesson. Thank you very much. This is Marshall A.C. Candiado. Thank you.